Okay, we'll start the class. So all of you tell, this board is visible and my voice is clear. Say yes or no. Is my voice is clear? So what is the chapter we are studying? Chapter name. Hello alkanes and hello arenes. So in the last class we completed physical properties, I think. In physical properties, solubility we completed, boiling point also we completed. Solubility and boiling point we completed. And boiling point of haloarenes also sometimes you ask. In boiling point, order I already given. Boiling point for haloalkanes I have given. In haloalkane, what is order of boiling point? Iodides are more boiling point. After that, bromides. After that, chlorides. And least is the chlorides. Why like this? Because iodine is the bigger surface area. More the surface area, more the van der Waals interactions and more the boiling point. That's why this is the order of boiling point for different haloalkanes, for different halogen atoms. If halogen atom is same, then boiling point depends on boiling point directly proportional to surface area. More surface area, more boiling point. So directly proportional to surface area or boiling point inversely proportional to branching. And branching is there, boiling point will decreases because branching decreases surface area, also boiling point decreases. This is all we completed in the last class. Now boiling point of some haloarenes also they will ask. Boiling point of boiling point of haloarenes. So haloarenes means, suppose we are taking dihaloalkanes. Like observe this. This is the benzene. Here chlorine. Here chlorine. Both are present at ortho position. Here both chlorines present at meta position. Both chlorine present at para position. So boiling point of dihaloarenes almost nearly same actually. Boiling point of dihaloarenes almost nearly same. But when you are observing the boiling point of these haloarenes, when orthodichlorobenzene, when you are observing, its boiling point will be nearly 453 Kelvin, whereas metadichlorobenzene will be 446 Kelvin, whereas para will be 448 Kelvin. Mostly values they don't ask, just for example I am giving. So nearly same, observe these values 453, 446, 448, all are nearly same. So the boiling point does not very large difference in haloarenes. But when we are coming to melting point, so melting point of this Orthodichlorobenzene will be nearly 249 Kelvin, whereas meta will be 246 Kelvin, whereas para will be 323 Kelvin. In melting point, para will be highest 323 Kelvin. In boiling point, ortho will be highest. So meta always gets least boiling point, least melting point. Just this order you have to remember. Para is always highest melting point. Why? Because para means both are opposite side. So this is a symmetrical nature. So due to its symmetry, it exhibits hard structure and it is high melting point. Some question they will ask why para is high melting point due to its symmetrical structure. Both are fluorines are opposite. It is a symmetrical structure. So that's why it will become hard when compared with other molecules. That's why it exhibits high melting point. This is order of melting points and boiling points in dihaloarenes. Another, sometimes they will ask density. Density of haloalkanes will be same like boiling point. Iodides are more dense. After that, bromides. After that, chlorides and chlorides. Of density, iodides are more dense molecules when compared with other molecules. Bromides, chlorides, chlorides. Chlorides are less dense molecules. So some one point I am writing here. Iodides and bromides. Iodides and bromides are more denser than water, whereas chlorides and chlorides are less denser than water. This statement, remember, chlorides and fluorides are less denser than water, whereas iodides and bromides are more denser than water. So that's why and chlorides will be float on water, and these are immersed in water. Remember this one. Iodides, bromides are more denser than water. Chlorides and fluorides are less denser than water. And the density order will be iodides are more dense, chlorides are less denser. So this is all about physical properties. This is all about physical properties. So the next one is, sometimes they will ask isomerism, but actually isomerism I already explained in the first PO. Just example I am giving, isomerism. Haloalkanes will exhibit haloalkanes exhibit chain, positional, optical and conformational. Isomerism. So isomerism, haloalkanes will exhibit what type of isomerism? They also exhibit chain isomerism, positional isomerism, optical and conformational. So these four isomerisms are shown by haloalkanes. How these will show? Examples I am giving. Position also goes. The first one is chain. The first one is chain. Chain isomerism, when we are observing, see these examples. C has 3, CH2, CH2, CH2Cl. So this is a chlorobutane, one chlorobutane. When it's chain isomerism, we are writing CH3, CH3, CH2Cl. Observe these two molecules. Here the first molecule has carbon chain length 4, but the second molecule has chain length only 3 carbon. This is the methyl chloropropane, and this is the chlorobutane. Both are same formula, but different structure. What is the difference in here? Carbon chain length is 4, carbon chain length is 3. And chain length is different. These are called which isomer? Chain isomers. That's why haloalkanes exhibit chain isomerism. These two are examples. Different carbon chain length. What are chain isomers? Differ in chain isomers differ in carbon chain length. So these are the chain isomers. Second, what they will exhibit? Also exhibit positional isomerism. Positional. What is positional isomerism means? Different position. Different position of functional group. And those are called positional isomerism. For example, you can take C has 3. What type 10 this is? 10 is very irritating. C has 2. CH2, CH2Cl. Another molecule CH3, CH2, CHCl, CH3. Observe these two molecules. It is also carbon chain length is 4. It is also carbon chain length is 4. Here chain is same. But what is the position of chlorine here? First position. But here chlorine position is second position. So when the position of functional group is different, those are called positional isomers. That means haloalkanes also exhibit positional isomerism. Similarly, what is the third one? Optical. Optical isomerism is shown by chiral compounds. Chiral means if carbon has 4 different substituents, that is called chiral carbon. For example, see this. C has 3, CH2, CH3, chlorine, hydrogen I written here. Right. See this central carbon. The central carbon is a chiral carbon or not? Above contains CH3 group. This side chlorine, below hydrogen. This side CH3, CH2 group. So all are different. This is a haloalkane molecule. So when all are different, it will exhibit optical isomerism. Since carbon is a chiral carbon, have 4 different substituents, optical isomerism. What are optical isomerisms? These are non-superimposable mirror image molecules. How to identify its configuration? Already told in the first PUC. Again I am explaining. When carbon has 4 different substituents, we have to give atomic number priority. Among this, chlorine is the highest atomic number. This we will take as first priority. Second will be this. 2 carbons are there here. This will be second priority. This will be third priority. And this will be hydrogen is the least atomic number, fourth priority. What is observation? Observation is from 1 to 2, 2 to 3. If this observation is clockwise, then that is called which isomer? R isomer. This is a R isomer. If you are writing its mirror image, central atom will be carbon, here CH3, here this is a chlorine atom, hydrogen atom, and this side will be CH2, CH3. So again when we are writing configuration, atomic number highest will be chlorine, second will be this group, third will be methyl group, fourth will be hydrogen. Observation is from where? 1 to 2, 2 to 3. So what is this direction? Clockwise or anti-clockwise? So it is a anti-clockwise. Anti-clockwise means what? Isomerism? S isomerism. So observe these 2 molecules. So these 2 are mirror images. If we have placed the first molecule in the mirror, it will be visible like this. So both are mirror image molecules. So one is R isomer, another one is S isomer. So whenever carbon is a chiral carbon, haloalkanes also will show optical isomerism. Optical isomerism already I explained. Practice that if anyone not understood. What is optical isomerism? They are non-superimposable mirror images. Both are mirror image molecules. If this molecule were placed on the above of this molecule, no matching is taking place. That's why these 2 are non-superimposable mirror images. So, how to identify configuration? Again I am telling. First we are giving atomic number priority. Highest atomic number is chlorine. Second, this is also carbon, this is also carbon. But it is again attached to another carbon. That's why this is second. After that 3 is the CH3. Least priority is the hydrogen. Observation is from 1 to 2, 2 to 3. This is a clockwise direction. That means it is a R isomer. Here 1 to 2, 2 to 3, anti-clockwise. This is S isomer. So R and S isomers are called optical isomers. After the optical isomerism, they also show last one, conformational isomerism. Conformational isomerism. Here optical I am writing, it is due to asymmetric carbon. Asymmetric means chiral. Optical isomerism is due to asymmetric carbon. Similarly, conformational isomerism. Conformational isomerism is due to free rotation. Due to free rotation of sigma bond. Due to free rotation of carbon-carbon sigma bond. For example, I am writing one haloalkane. He has 3 for example, dihaloalkane I am taking. So this is the CH2Cl. This is the CH2Cl. So it is the carbon-carbon single bond. This is the sigma bond. Sigma bond can be freely rotate. So due to free rotation, they will exhibit conformational isomerism. Conformational isomerism we can represent in 2 techniques. Saha's projection also, Newman projection also. What we will do in Saha's projection, we will take vertical line. This is the carbon, this is the carbon. We are writing Y here, also writing Y here. Place hydrogen, 2 hydrogens on this. Third one is the chlorine. Here also 2 hydrogen. Third one is the chlorine. Here both are white. That means this is which molecule? Eclipsed isomer. All are first PU I am explaining. This is eclipsed isomer. What is another possibility? If here I am writing Y and here I am writing ulta Y. Here 2 hydrogens placed and here Cl atom, and Cl atom I am placing here hydrogen, hydrogen. When one is Y and one is ulta Y, then it is called what? Staggered. So this is the conformational isomerism. In haloalkanes, whenever carbon-carbon single bond is there, so it will freely rotate. They will exhibit conformational isomers. If both are on same line, that means Y and Y eclipsed. One is Y and one is anti-Y. That is called staggered. This is about isomerism. What isomerism exhibited by haloalkanes? Haloalkanes will exhibit chain isomerism, positional isomerism, optical isomerism, and conformational isomerism. Chain isomerism is due to different carbon chain length. Positional is due to different position of the functional group. Optical due to presence of chiral carbon, asymmetric carbon. Conformational is due to carbon-carbon single bond free rotation. Number of examples are given in the first PO. Here also examples are given. Just with 2 examples you can easily understood. Right. So these are the physical properties completed. Next, we'll start chemical properties. Chemical properties of haloalkanes and also halogens also we'll see. Remember all haloalkanes will always show three types of properties. Haloalkanes will always show three types of properties. This pen is very irritating me. Three types of properties, that is, first one, reaction with metals. Reaction with metals. Second one is nucleophilic substitution. Nucleophilic substitution. Third one is elimination. Third one is elimination reaction. Total how many types of reaction will show by haloalkanes? Haloalkane shows three types of properties. First one is reaction with metals. Second one is nucleophilic substitution. Third one is elimination. One by one we'll see. First we'll see reaction with metals. Reaction with metals. This is the first property of haloalkane. Haloalkanes will combine with metals. How they will combine? We will see. Whenever haloalkanes combines with metals, metals means number of metals we take, but in for our syllabus there are two important metals. One is the sodium, another one is the magnesium. So first we will say with sodium. With sodium, sodium symbol is Na. With Na, haloalkanes will combine with Na. So observe this. What is the symbol of haloalkane? Rx. If it is combining with sodium. So this reaction also actually we completed in the first PO. You can remember now. I am taking 2 moles of haloalkane. Rx means haloalkane. This is also Rx means haloalkane. I am taking 2 sodium. In presence of here, we are using dry ether. So 2 moles of haloalkanes combines with 2 sodium in presence of diether. What will be takes place? This totally will be removed like this. What is removing? So 2NaX is removing, and what is the remaining? Alkyl combines with alkyl. R means carbon. This is also carbon. This is nothing but hydrocarbons. Alkanes we get. Have you remembered this reaction? This reaction name is Woods reaction. whenever haloalkanes combines with sodium in presence of dry ether to produce alkanes, the reaction is called Woods reactions. So number of example will take. Statement I am writing: haloalkanes combines with sodium in presence of dry ether produce alkanes. So this is the statement of Woods reaction. Haloalkanes combines with sodium in presence of dry ether produce alkane. So it is the in hydrocarbon chapter of first PUC I have given in the preparation of alkanes. This reaction is given. Maybe all of you forgot it, but in the first PU I already told actually. First PU basics are continuously will come in the second PU. So that's why first PU is also important. So Woods reaction. What is Woods reaction? Haloalkanes combines with sodium in presence of dry ether produce alkanes. Examples will say, I am taking CH3. Examples: CH3, CH2, Cl. It is a haloalkane, combines with how many sodium metal? 2 sodium metal plus another haloalkane, Cl, CH2, CH3. In presence of what is the catalyst? Dry ether. So what will remove? So this continuously will remove 2 NaCl will be removed. On removing 2 NaCl, what we get? This alkyl group will combine. The product will be CH3, CH2, single bond, CH2, CH3. So butane will form. So this is the Woods reaction. So 2 moles of haloalkanes combines with sodium metal. So NaCl will be removed. We get combination of alkyl and alkyl group. So we get alkane. Now what is the drawback of this Woods reaction? Observe here. We are taking haloalkane. This haloalkane and this haloalkane both must be same. That means here 2 carbon, here 2 carbon. On combining, how many carbons we are getting? 4 carbons. So that means the product is always even number carbons. All of you understanding? In Woods reaction, the product is always even number carbon atoms. So we cannot form odd number of alkane. Only we can form even number of carbon atoms alkane we can form. That means this reaction gives alkanes having even number that means in bracket it is also called symmetrical. Even number means symmetrical. This reaction gives alkanes having even number carbon atoms. Even number carbon atoms. That means it cannot use for the preparation of odd number alkanes like propane. Propane means 3 carbons. So propane we cannot prepare by Wood reaction. We can prepare ethane, but we cannot prepare propane. So that means Wood's reaction drawback, if anyone is asking, in this reaction we can only prepare symmetrical alkanes. Only prepare symmetrical alkanes. We cannot prepare unsymmetrical alkanes. So that is the Wood's reaction. I hope all are understand. So the first property of haloalkane is reaction with metals. The first metal we have taken sodium. Whenever haloalkanes combines with sodium, we get alkanes. The reaction is called Wood's reaction. The alkane must be symmetrical alkanes we get, unsymmetrical alkanes we don't get. Because when two alkyls are combining, that must be product is even number. So this is haloalkanes reaction with sodium. Not only haloalkanes, another reaction with sodium is fatigue reaction. Fatigue reaction. What is fatigue reaction? Haloarenes. Haloarenes combines with sodium in presence of dry ether. We get biphenyl. We get biphenyl. So this reaction is called fatigue reaction. What is Wood's reaction? Haloalkanes combines with sodium is Wood's reaction. In place of haloalkanes, if we are using haloarenes, haloarenes means what? Benzene has halogen. So this is haloarene. If it is combining with two sodium metal, taking two haloarenes. So this is a haloarene, this is a haloarene combining with two sodium in presence of catalyst is dry ether. What we get? Again, what will remove here? So this 2 NaCl will be removed. On removing 2 NaCl, what we get? This benzene will combine. The product is called biphenyl. This is benzene. It will combine with another benzene. Product name is biphenyl. Reaction name is fatigue reaction. Haloalkanes with sodium, Wood's reaction. Haloarenes with sodium, fatigue reaction. In Wood's reaction, alkanes will form. In fatigue reaction, biphenyls will form. Biphenyls will form. Finally, another equation. Third one, Wood's fatigue. Number is not given, maybe. Number is given or not? Okay, not given. Yes, first one is Wood's reaction. Second one is fatigue reaction. The third one is Third one will be Woods fatigue reaction. Third one will be Woods fatigue reaction. What is Woods fatigue reaction is both haloalkanes and haloarenes. Both haloalkanes and haloarenes combines with sodium in presence of dry ether. We get alkyl. So see this reaction. So one is haloalkane I am taking, haloarene I am taking. So this is the haloarene combines with 2 sodium. Another I am taking haloalkane. So anything like ClCH3. So this is haloalkane, this is haloarene in presence of dry ether. So what will be removed? This totally 2 NaCl will be removed like this. On removing 2 NaCl, what we get? Remaining is benzene is there. On benzene, alkyl group will come. Alkyl is here, methyl group. CH3 will come. So this is alkyl benzene. Reaction name is Woods fatigue reaction. So with sodium metal we have seen. So with sodium metal there are 3 reactions. Haloalkanes also combines with sodium. Haloarenes also combine with sodium, or both haloalkanes and haloarenes combines with sodium. If haloalkanes combining with sodium, reaction name is Woods reaction. Haloarenes combining with sodium, reaction name is fatigue reaction. Or one haloalkane and one haloarene combining, reaction name is Woods fatigue reaction. So this is the reaction with sodium. We are taking reaction with metals. The first metal we have used sodium metal. So next is the magnesium, that we will see in the next class. So up to here, everybody understand, I hope. Practice this. Thank you very much. You can leave now.